Hello and welcome to another video. In this video, I'll be going through paper 2 of the 2018 Specimen papers. This set of papers was used as mocks in preparation for the 2019 A-level exams. In my opinion, these are more challenging than the sample assessments and more in line with the official exam papers. If you did have a go at these, let me know how you went and how you think they compare with the sample assessments or other sets of papers that you might have done. As always, the paper and the mark scheme are linked in the description so you can have a go yourself. But without further ado, let's get straight into the questions. Question 1 has a diagram and it says figure 1 shows a circle with a center O. The points A and B lie in the circumference of the circle. The area of the major arc, shown shaded in figure 1, is 135 centimeters squared. The reflex angle AOB is 4.8 radians, so that would be that angle in here. Find the exact length in centimeters of the minor arc AB, giving your answer in the form A pi plus B, where A and B are integers to be found. So that would be this length in here, this minor arc. Okay, so firstly we can start with the formula of the area of a sector in radians. So that looks like this. So the area of a sector equals a half times the angle in radians times the radius squared. And if you haven't seen that before, you could always start with the area of a sector in degrees, which you should know, and you end up with this formula here. So that's what we're going to start with. And then we're told angle AOB equals 4.8 radians. And we're also told the area of that sector is 135 centimeters squared. So we could set those two things equal to each other. So a half times the radians, which is 4.8, times the radius, which is what we're looking for, so the radius squared, equals 135. So I've just taken that formula and set it equal to the area they've given us. So half of 4.8 is 2.4 times the radius squared equals 135. Divide 135 by 2.4. Let's do that on a calculator. So 135 divided by 2.4 gives us 56.25, and then we take the square root of that answer to get the radius, and we get 7.5. So the radius of this circle is 7.5 centimeters. And now to find this minor arc length. Well, what is a radian? It's the angle you get when you wrap the radius around the circumference. So this 4.8 radians literally means we've wrapped the radius around this major arc 4.8 times. So to find the length of that minor arc, we need this angle in here, multiply it by the radius, and we'll have the length of that minor arc. So we need that angle in there. We're talking about radians, remember? So there are 2 pi radians in a circle. So this angle is going to be 2 pi take 4.8, and then if we multiply that by 7.5, we'll have that length. So the arc length, the minor arc, is going to equal 2 pi take 4.8, which is the angle of the arc, multiplied by the radius, which is 7.5. And now we needed it in the form A pi plus B. So let's multiply this 7.5 by 2 pi. That will be 15 pi. 4.8 times 7.5. I'm feeling lazy, so let's just do that on a calculator. 4.8 times 7.5, and we get 36. So this will be negative 36. So we have that in the form they wanted, A being 15 and B being negative 36. And that was question 1 for 4 marks. There'd be 1 mark for stating the formula of the area, for finding probably 2 marks for finding R, and then 1 mark for finding the length of the minor arc. Question 2a says, given that theta is small, use the small angle approximation for cosine theta to show that 1 plus 4 cosine theta plus 3 cosine squared theta is approximately equal to 8 take 5 theta squared. Okay, so let's start A down here and start by writing down the small angle approximation for the cosine of theta. And this is in your formula booklets as well, in case you forget it. So the small angle approximation for the cosine of theta says that cosine of theta can be approximately equal to 1 take theta squared on 2 when theta is small, and theta must be in radians. There is a formula for degrees, or there might be a formula for degrees, but it won't look like this. It'll look different to that if it were in degrees. So for this formula to work, theta must be in radians. And now let's write down the expression they gave us. So that was 1 plus 4 cosine theta plus 3 cosine squared theta. Let me just check I got that right. Yep, so now we need to show that that is approximately equal to 8 take 5 theta squared. So we can say this is approximately equal to 1 plus 4, and then when we get to the cosine of theta, we can substitute in this 1 take theta squared on 2. So substitute that in, and then we have plus 3 multiplied by cosine squared theta, and now we're going to take this small angle approximation and square it. So this will be 1 take theta squared on 2 all squared. Next, we can start simplifying this. So expand these brackets out. 4 times 1 is 4. 4 times theta squared on 2. Well, 4 divided by 2 is 2, so this will be negative 2 theta squared. Plus 3, and now we need to expand these brackets out, these squared brackets. So this will be 1 take theta squared on 2 times 1 take theta squared on 2. And we can use FOIL to expand those out. So this is equal to, I didn't need that approximation there actually. So when we say approximately equal to in the first line, then we can just write an equal sign. So now expand these brackets out. So 1 plus 4 is 5. Take 2 theta squared plus 3 multiplied by, using FOIL, as I said, 1 times 1 is 1. Outers, 1 times negative theta on 2. That'll be negative theta on 2. Same for the inners, negative theta on 2. And the last will be plus theta to the power 4 on 4. Okay, because both terms are negatives, and theta squared times theta squared will be theta to the power 4. All right, now we can expand those brackets out. So we'll have 5 take 2 theta squared plus 3 times 1 is 3. Take, and now we can actually simplify this first. So theta squared on 2 take theta squared on 2. That's like negative a half take a half. So that'll just be negative theta squared. So negative theta squared times 3, that will be negative 3 theta squared. And then we have 3 times theta to the power 4 on 4. So that'll just be 3 on 4 theta to the power 4. Okay, so we've expanded those brackets out, then keep simplifying. So 5 plus 3 is 8. And negative 2 theta squared take 3 theta squared, that will be negative 5 theta squared. And then we have this plus 3/4 theta to the power 4 on the end. Now let's go back to the expression they asked us to find. It was 8 take 5 theta squared. But we have this 3/4 theta to the power 4 on the end. Well, it turns out we can just say that because theta is small, theta to the power 4 is so small that we don't have to worry about it. Whereas theta squared still gives us some degree of accuracy. If we're to add that theta squared or take that theta squared away from the answer, it still has an impact on the accuracy of our answer. Whereas theta to the power 4 really is not going to make any difference to our answer in the end. So we can actually say that this is equal to 8 take 5 theta squared. And the mark scheme doesn't even account for this. You can just leave it off. You don't actually need to give an explanation as to why you leave that theta to the power 4 out of your answer. You can just finish with this. And as long as you're understanding why you're leaving that off, then that's fine. You don't actually have to write down why you're doing that. And hopefully that makes sense. So think about if we had, say, theta equal to 0.1, for example. 0.1 to the power 4, well, that's a 10,000th of a degree. So hopefully you can see that theta squared will only be 100th. So that kind of still is having an impact on the accuracy of our answer, changing the degree of accuracy, whereas theta to the power 4, really, we don't have to worry about that. All right. So hopefully I explained that okay as to why we're ignoring this theta to the power 4. And anyways, that's the answer for part A for 3 marks. The question goes on and it says Adele uses theta equal to 5 degrees to test the approximation in part A. Adele's working is shown below. Using my calculator, 1 plus 4 cosine of 5 degrees plus 3 cosine squared of 5 degrees equals 7.962 to 3 decimal places. Using the approximation 8 take 5 theta squared gives 8 take 5 times 5 squared, which is negative 117. Therefore, 1 plus 4 cosine theta plus 3 cosine squared theta approximately equal to 8 take 5 theta squared is not true for theta equal to 5 degrees. And part BI says identify the mistake made by L in her working. Well, she's used degrees for her angle and she needs to change that to radians for this formula to work. So we can just write that down for part BI. So angle needs to be in radians when using the small angle approximation. And we can actually find what 5 degrees is in radians. So to change degrees to radians, we multiply by pi on 180. So this is pi on 180 times 5. And if you do that calculation, well, you could just simplify it. 180 divided by 5, that's 36. So this is actually pi on 36 radians. And part 2 says show that 8 take 5 theta squared can be used to give a good approximation to 1 plus 4 cosine theta plus 3 cosine squared theta for the angle of size 5 degrees. Okay, so this is going to involve putting this angle in radians into our approximate expression. So we'll take 8 take 5 theta squared, which is pi on 36 squared. And let's find what that is. So in our calculator, we can do 8 take 5 times pi on 36. And that is squared. And we get an answer of about 7.962 to 3 decimal places. And then if we go back to the question, she's found that for the original expression for us already, so we don't have to worry about that one. But we can just say that it is equal to the answer when we use that expression, so it is a good approximation for an angle of size 5 degrees. So we can go ahead and write that down in a sentence or two. So we can say which is the same to 3 decimal places of accuracy as 1 plus 4 cosine theta plus 3 cosine squared theta for 5 degrees. So the question says show that it's a good approximation, and we've done that. So that's 2 marks for part B, 3 marks for part A, and 5 marks in total for question 2. Question 3 says a cup of hot tea was placed on a table. At time t minutes after the cup was placed on the table, the temperature of the tea in the cup, theta degrees centigrade, is modeled by the equation theta equals 25 plus ae to the power of negative 0.03 t, where a is a constant. The temperature of the tea was 75 degrees C when the cup was placed on the table, and part A says find a complete equation for the model. Okay, so using that information, we can go ahead and solve for this constant A. So we can say for part A, when t equals 0, theta will equal 75 degrees centigrade. So therefore 75 equals, and now let's have a look again at the expression. So if t was 0, e to the power 0 would just be 1. So this part of the equation would just be a times 1, and we'll have 25 plus a. So 75 is going to be 25 plus a. So therefore a is going to equal 75 take 25, which will be 50. So therefore we can say theta equals 25 plus 50 e to the power of negative 0.03 t. So we have that complete equation. Let's go on to B now. B says use the model to find the time taken for the t to cool from 75 degrees to 60 degrees, giving your answer in minutes to one decimal place. Okay, so theta is now 60 degrees. So for part B, we're going to start with when theta equals 60 degrees centigrade. 60 will equal 25 plus 50e to the power of negative 0.03 t. So I'm just replacing that theta with 60 here, and now I can solve for t. So then take 5 from the left hand side, and I'll just flip it around. So then we can say that 50 e to the power of negative 0.03 t equals 60, take 25, that's 35. And then e to the power of 0.03, negative 0.03 t equals 35 divided by 50. And then we can take the natural log of both sides. So the natural log of e effectively cancels out that e. So on the left, we'll just be left with 0.03 t equals the natural log of 35 on 50. And then t is going to equal whatever this is divided by negative 0.03 t. So the log of 35 on 50 multiplied by 1 on negative 0.03. Okay, and then we can just put that into a calculator. So the natural log of 35 on 50 divided by negative 0.03. And we get an answer of 11.889 approximately, 11.889. And the question said to, what did it say, to one decimal place in minutes. So t was in minutes already, I think. T is, it says here, at time t minutes. So t is already in minutes. So to one decimal place, this is going to be 11.9 minutes. Okay, so that was part B. Part C says 2 hours after the cup was placed on the table, the temperature of the tea was measured at 20.3 degrees. Using this information, evaluate the model explaining your reasoning. So we could find the temperature that the model gives us 2 hours after the cup was placed on the table. So T would equal 120, and compare it to the measured temperature, and then comment on the accuracy of the model. So what I'm going to do for part C is to say when t equals 120, theta will equal 25 plus 50 e to the power of negative 0.03 times 120. And then we can figure that out. So 25 plus 50 multiplied by e to the power of negative 0.03 times 120, and we get 26.36 or 26.4 degrees centigrade, and the measured temperature was 20.3 degrees. So 26.4 is not approximately 20.3, so that's what I'd say first. So 26.4. So 26.4 is not approximate to 20.3 degrees. And actually we could look at this model and say that the temperature, it will be unreliable when the temperature is actually below 25, and I'll demonstrate that in a minute. But overall we can say it's not accurate for large values of t. So the model is not accurate. So the model is not accurate or appropriate, whichever word is better there, for large values of t or when the temperature is below 25 degrees. So if we rearrange this equation, we get e to the negative 0.03 t equal to theta take 25 on 50. And now e to the power of anything cannot be a negative number. So even if this is a negative, this will not be, the result of this e to the power of something will not be a negative value. So if we're getting, say, 20 take 25, this would be a negative, and therefore this equation will not have any solutions. So I could just say as we get this equation, it has no solutions. It has no solutions when theta is below 25. So for the 4 marks, I don't think you have to add that. The main point is you need to say that the model is not appropriate. Well, firstly, you need to find this temperature, 26.4. It's not approximate to 20.3. Therefore, the model is not appropriate for large values of t. Okay, so that was part C for 1 mark. Part A was 1 mark, part B was 2 marks, so part 3 in total was 4 marks. Question 4, part A says, sketch the graph with equation y equals the absolute value of 2x take 5, stating the coordinates of any point where the graph cuts or meets the coordinate of the axes. Hopefully you've seen a graph of absolute values before, like this, and you'll know it looks generally like this, where it has no negative values for y. So all of the values are positive, and it has the same gradient going, into the negative x and into the positive x. So we know the general shape it should take, and we can figure out where the x-intercepts are, what the gradient is, and that allows us to sketch it quite quickly. So for part A, first we need to draw our axes, and it'd be nice if they provided graph paper, but I have to do with these lines. So give yourself enough space on your page, draw a nice big axes, label them x and y, and then give yourself a scale. So 1, 2, 3, 4, 5, 6, 7, maybe go up to 10. Don't exactly know what the graph will look like at this stage, but I'm hoping this is enough space. We can always change it again if it's not. So I'll go up to 7 on the y-axis, and maybe just every second point on the x-axis to save time. And again, we don't really need to draw in the negative values on the y-axis. Let's have a look now. Y equals the absolute value of 2x take 5. Well, we know then that the y-intercept will be 5. If this wasn't the absolute value, you'd know the y-intercept will be negative 5. But because we're not looking at the negatives, we know that the y-intercept will be positive 5. The gradient is 2, and when y equals 0, x would be 5 on 2, right? So if we solved this for y equal to 0, we'd have x equal to positive 5 divided by 2. So we know the x-intercept as well is 2.5. And the gradient, as I said, is 2. So going down here, we need to go 1 across and then 2 down. So we could draw a point at 1, 3, and then 2 down, 1 across again. So another point at 2, 1. And by then you have enough information to draw in a straight line from the x to the y-intercept. We didn't really need those intermediate points, but maybe it helps, maybe not, I don't know. And then again, going up the other side, go up 2 across 1, up 2 across 1, etc. And then after you've got 1 or 2 points, you can draw in the other line. Okay, so there's our graph of y equal to the absolute value of 2x take 5. Okay, so there's our graph with everything labeled. Oh, we had to label the intercepts as well. So this was 0, 5, and this was 2.50. Okay. All right, part B says find the values of x which satisfy the absolute value of 2x take 5 greater than 7. Okay, so for part B, we're looking to solve 2x take 5 equal to 7. Now you can do this either algebraically or with the help of your graph. So looking at the graph, what does this actually mean for this graph to be, whoops, I've written that wrong, sorry. This should be greater than 7, not equal to. So what does that mean for this graph to be greater than 7? Well, if we drew a line equal to 7, y equals 7 on this graph, it would be up here. I might just do that in a different color. So it would be up here, right, at y equals 7. All right, so we're looking at the x values. If we went down to the x axis, we're looking for the x values where this graph becomes greater than 7. So you can see at this x value, this graph is now greater than 7, and at this x value, less than that, the graph is greater than 7. So we're looking for those 2 points. And as I said, we can do this algebraically as well. So to get rid of absolute value symbols, one way you can do this is to say that this is going to be 2x take 5 greater than 7, as it states, or you need to introduce a negative. So one way to write that is negative 2x take 5 greater than 7. And then to get rid of this negative 1 on the left-hand side, we divide it by the right-hand side. And remember, when you divide by a negative, divide or multiply by a negative with inequality signs, you need to flip the inequality around. So this is the same as saying 2x take 5 less than negative 7. So now we have 2 inequalities we need to solve. So let's start with the left-hand side. We could add 5 to the right-hand side. So this will be 2x greater than 7 plus 5 is 13. And then x is greater than 6.5, 13 divided by 2. Or we have this case where we have negative 7. So 2x is less than negative 7 plus 5, that's negative 2. So x is less than negative 1, negative 2 divided by 2. So we have our 2 inequalities there. X is greater than 6.5 and x is less than negative 1. And if we go back to the graph, we can see that that will fit, right? This looks about 6.5 and this looks like it would be about negative 1 here. The graph isn't completely accurate. We haven't done it perfectly to scale, but we can see we're in the right ballpark. And I'd be pretty confident if I saw that graph and I saw my answers, I'd be pretty confident they're correct. So that's the way the graph can help you if you're also solving this algebraically. Part C says find the values of x which satisfy the absolute value of 2x take 5 is greater than x take 5 over 2. Write your answer in set notation. Okay, so part C, let's do part C down here. Again, I'll try to solve this algebraically. So it was 2x take 5 greater than x take 5 on 2. All right. So again, as I said before, we can do the positive solution. So 2x take 5 greater than x take 5 on 2, as it says there. Or we can introduce the negative. And I might just do this in one step. So we get 2x take 5. We have to flip that inequality around because we're dividing by negative 1. Then we get negative x plus 5 on 2. And now we have our 2 inequalities we need to solve. So for this one, we could subtract that x from the left-hand side. So we'll have 2x take x is just x. And that's greater than negative 5 on 2, or negative 2.5, plus 5 will be positive 2.5. Or we have this case over here where we have 2x plus x. So we'll have 3x on the left-hand side. And then 2.5 plus 5, which is 7.5. And then 7.5 divided by 3, that's 2.5 as well. So we actually get an answer that says x is greater than 2.5 and x is less than 2.5. So that's pretty much all of the real numbers, except for one, which is 2.5. It doesn't say x is equal to 2.5. So the set of values is going to be x belonging to the real numbers, so any real number, except x equal to 2.5. So x does not equal 2.5. and that is how it would be written in set notation with those curvy brackets. There are slightly different ways to write that, and there will be a number of different ways of writing on the mark scheme if you want to check that out. But there you go, that's part C, and that was for 2 marks, total of 6 marks for question 4. Okay, question 5 says the line L has equation 3x take 2y equals k, where k is a real constant. Given that the line L intersects the curve with equation y equals 2x squared take 5, at 2 distinct points, find the range of possible values for k. Okay, so we have a straight line and we have a quadratic, and we want a range of possible values for k. So what is this equation saying? Now I'm going to find this easier if I rearrange this in terms of y. Now you might not need to do this, but this is just the way that I'm used to. So I'm just going to rearrange this so that it's y equals something. So if we take that 3x from the right hand side, and we'll have plus k, and then divide by -2. So this would actually be positive 3 on 2, take k on 2. So we have a straight line of 3 on 2x take k on 2. So what that's saying is k is part of the y-intercept of this straight line. And I'm actually going to find this easier if I draw a quick sketch. Now it might not be accurate, but it's going to give me some idea of what's going on here. So a little sketch to help your understanding is always helpful. So we have some quadratic, and its axis of symmetry is the y-axis because we don't have an x term in there, and it's a positive quadratic, so I know it's going to be going up like that. Also, I know the y-intercept will be -5, so it'll cross the y-axis down here at -5. And then we have a straight line with a gradient of positive 3 on 2. So we'll have a straight line going through this graph somewhere, but we don't know where the y-intercept is. So it could be like this, for example. It'll be a bit steeper than that actually, because the gradient is 1.5. But anyway, you get the idea. And by drawing this graph, I actually can see what's going on here now. So the range of possible values for k will be where are the positions where this line can cut that graph in 2 places. Well, if the straight line was down here, it wouldn't cut the graph at all. So there's going to be some minimum value of k. There won't be a maximum, because as long as the graph is going up here somewhere, then it will always cut the graph twice, but there'll be a minimum value for k. So that's what we're going to try to find here. If this graph does not cut the quadratic at all, if it was down here as I was saying, then these 2 equations, this quadratic and this straight line, will not have any solutions. In other words, there'll be no point where they intersect, therefore there'll be no point where they're equal. So we can say the inverse of that and say that there'll be solutions for k when these 2 things are equal, when the straight line does intersect the quadratic twice. Right? So there will be solutions for k when 2x squared take 5 is equal to this straight line here, this equation for this straight line here. So that's where I'm going to start. So we can say when the lines intersect, we'll set those 2 equations or expressions equal to each other. So 3 on 2x take k on 2 is going to equal 2x squared take 5. And then what we want to do is to simplify this into a quadratic equal to 0. So the first thing I might do is multiply through by 2 to get rid of these denominators. So then we'd get 3x take k equal to 4x squared take 10. And then subtract these things from the left hand side. So, and then I might flip it around. So we'll have 4x squared take 10, take 3x plus k equal to 0. So I've just taken that 3x and added that k to the same side as the 4x squared take 10. And then because I know that k is some constant, I'll put that together with that negative 10. So then we'll have 4x squared take 3x plus k take 10. I think that's a neater way of writing it. So this is going to be some constant number so that this equation has a solution. Remember, if this equation does not have a solution, the line is down here and it does not intersect the quadratic. So we need this equation because they've told us the line intersects the curve. Therefore, we need this equation to have some solution. So to find the solutions to this equation, we can use the quadratic formula. So that says that x is equal to negative b plus or minus the square root of b squared take 4ac over 2a. And now you might say, well, why don't we try to factorize first? So you could try to factorize this, but this k minus 10 is going to make it, basically impossible to think of solutions to this. So it's easier to jump straight to the quadratic formula and then plug the coefficients in. So this is going to be negative b is negative 3, so this is going to be 3 plus or minus b squared, which is 9, take 4 times a, which is 4, times c, which is k, take 10. And this is over 2 times 4. Okay, so what do you know about the discriminant of the quadratic formula? You know that it has to be positive for there to be real solutions to this quadratic. So we can take this discriminant in here, this 9 take 16 times k take 10, and say that must be greater than 0 for this line to cut this quadratic. So that's what my next line is going to be. 9 take 16 times k take 10 must be greater than 0. Now, why not greater than or equal to 0? Because if it was equal to 0, there'd only be one solution, and the question says there are two distinct points where the line cuts the quadratic. That means that this quadratic here must have two distinct solutions. Therefore, this discriminant must be greater than 0, not greater than or equal to. So then let's go ahead and solve this for k. So expand those brackets. 9 take 16k plus 160 is greater than 0. Then negative 16k is greater than negative 169. So I've just taken that 160 and that 9 from the right hand side. And then k is greater than 169 divided by 16. Let's put that into a calculator. So 169 divided by 16, 10.5625, and those negatives cancel out. So this is 10.5625. And I've almost forgotten a step there. So when we divide by a negative, remember we need to flip the inequality around. So this is actually going to be k less than 10.5625. And so that's going to be the range of k. So the range, just to finish off, of k is k less than 10.5625. And you can actually check if that's realistic. So if we just round that off to 10, say, just to make it easier to estimate, what would this line be? This would be 3x on 2, take 10 divided by 2, which is 5, right? So the y-intercept there would be negative 5, which is the y-intercept of the quadratic. So if this line was going through that point, you can see we would have two intercepts. So, and actually the minimum value of k is a bit bigger than 10, so it's just above that negative 5. So this would be a bit more than negative 5, so that the line cuts the quadratic in two places. So that makes sense in terms of the question, and it passes the reality check or the common sense test. There's always these little tests you can do at the end of a question to see if it makes sense in terms of the question. If you got something like, a large number, or even if you got that inequality around the wrong way, like I did briefly for a second, you could go back and check, well, if this was greater than 10, if this was say 20, then that y-intercept would be down here and it wouldn't make sense. So there's always these little checks you can do to make sure that your answer is correct, or you can be confident in your answer. So that was question 5 for 5 marks. Question 6 starts with a diagram, and it says figure 2 shows a sketch of the curve with equation y equals f of x, where f of x equals 8 take x log of x, and x is greater than 0. The curve cuts the x-axis at the points A and B, and has a maximum turning point at Q as shown in figure 2. So A and B and Q. Part A says find the x-coordinate of A and the x-coordinate of B. Alright, so A and B are where this curve cuts the x-axis. So this will be where y equals 0, or f of x equals 0. So we can start with that. So for part A, when f of x equals 0, we'll have 8 take x times the log of x equal to 0. And then we have 8 take x equals 0, or the log of x equals 0. And then solve each of these. So if 8 take x is 0, then x must equal 8. Or if log of x equals 0, then x must equal 1. So the log of 1 is 0. So then look back at the graph. Well, a must be 1 and b must be 8. So we have the x-coordinates of a and b. A is x equals 1 and b is x equals 8. Okay, so that was part A. Part B says show the x-coordinate of q satisfies x equal to 8 over 1 plus the log of x. Alright, so what's special about q? They've told us it's a maximum turning point. And what do you know about the maximum turning point of a curve with relation to calculus? That is where the derivative equals 0, right? The tangent is a flat line, so the slope of the tangent is 0, therefore the derivative will be 0. So this is going to involve finding the derivative of f of x, setting that equal to 0, and finding x. So we can say for part B, at q, f prime of x is going to equal 0. And I'll just write down f of x again. This was 8 take x times the log of x. And I might find this easier to take the derivative if I expand those brackets out. So this is going to be 8 times the log of x, take x, log x. So therefore f prime is going to be the derivative of this. Now the derivative of the log of x is 1 on x. So the first term here will be 8 on x. And the second term, we need to use the product rule. So the product rule says that the derivative of two functions together like that multiplied. So if we have fg, the derivative of that is f prime times g plus f times g prime. So we can take the derivative of f, in this case is x, which is just 1, and we need to subtract all of this. So I'm going to write a negative and then put this in brackets to make sure I remember to expand that negative across all the terms. So f prime was x was 1, as I said, and then we just have the log of x. And then the second term is just f, which is just x, and then the derivative of the log of x, which is 1 on x. And that term there will just be 1. X on x will just be 1. So here we get 8 on x, subtract the log of x, take 1. So I've expanded that negative to this term here, which we said was 1. Okay, so we've got f prime, and we said this would equal 0 at q. So let's write that in now. So we've got 8 on x, take the log of x, take 1, equal to 0. And remember, we need it in terms of x. So we could add this log of x and this negative 1 to the right hand side. So then 8 on x equals the log of x plus 1. And then multiply by x, so this will be 8 equal to x times the log of x plus 1. And then divide by the log of x plus 1. So then x is going to be 8 divided by the log of x plus 1. And let's go back to the question. That's what they needed. Oh, sorry, this one here, x over 1 plus the log of x. Oh, so they've just written that denominator around a different way, but that's exactly the same thing. So that was question B. Part C says show that the x-coordinate of Q lies between 3.5 and 3.6. Okay, so the turning point of a graph, if you think about the derivative, if we take the tangent at this point here, before Q, that will clearly have a positive slope, positive gradient. And then if we looked at the tangent after Q, it would clearly have a negative slope, right? So around a turning point, the sign of the derivative will change. Okay, so we can use that idea. We can find the derivative at 3.5, the derivative at 3.6, and if the signs change, then we know there must be a turning point in between them. So we could start by finding f prime of 3.5. And remember, f prime was 8 on x take the log of x take 1. So this is going to be 8 on 3.5. Take the log of 3.5. Take 1. And then put that into your calculator. So 8 divided by 3.5. Take the log of 3.5, take 1, and we get 0.03295, etc. So, 0.03 will do. So 0.03, etc. So that's a positive. Then let's find f prime at 3.6. This will be 8 on 3.6. Take the log of 3.6. Take 1. Put that into the calculator. So 8 divided by, take the log of 3.6, take 1, and we get a negative 0.05. So negative 0.05, etc. So all we really need to show there is the signs changed, and therefore there must be a turning point. So let's state that in a couple of sentences. So gradient changes from positive to negative, or the signs change, however you want to state that. And so therefore there must be a max between 3.5 and 3.6. Oh, and that's the other thing. If it's going from positive to negative, that would be a max. If it's going from negative to positive, that would be a minimum. So that's the other reason that it's a maximum. So it goes from positive to negative. All right, so that was part C. Part D says use the iterative formula, x sub n plus 1 equals 8 over 1 plus the log of x sub n, where n is any natural number, with x1 equal to 3.5, to find the value of x sub 5 to 4 decimal places. And part 2 says find the x-coordinate of Q accurate to 2 decimal places. Okay, so this is the equation we found earlier, and x sub 1 is 3.5. Okay, so let's firstly write that down. X sub n plus 1 is equal to 8 over 1 plus the log of x sub n, and x 1 equals 3.5. So that's x sub n. Okay, so we could just do all of this on a calculator until we get to x sub 5. I don't think we really need to write down all of our answers. So I might just clear this. Let's firstly put in x sub 1. So we'll have 8 divided by 1 plus the log of 3.5. And we get 3.5511. Then do it again. And actually, if you have this entry button on your calculator, you can actually get that same formula without having to type it out again. And then just input answer. Makes it slightly quicker. Then we get 3.52, and then do the same thing, entry, and then it already has the answer in it. So what are we up to? That was x2, that was x3, this will be x4, and then we need to do it one more time to get x sub 5. Okay, so 3.5340, and the question said to 4 decimal places, I believe. Yes, 4 decimal places. So x sub 5 to 4 decimal places will be 3.5340. Okay, so that was part I. And part 2 again was find the x coordinate of q to 2 decimal places. So part 2. So for part 2 we could just keep doing this iteration. So entry equals, entry equals, entry equals. So do it as many times as you think is necessary, but you can see once you do it a few times, you recognize that third decimal point stays at 5. So no matter how many times you do it, all that's changing is these last digits here. So this 5 here is clearly staying the same between each answer. So to 2 decimal places, we can see this is going to round off to 3.54. So at q, x equals 3.54 to 2 decimal places. So that just required our further iteration or further iterations, just to show what you need to round that off to do 2 decimal places. Okay, so that was question 6 for 9 marks. Question A was 1, question B was 4, question C was 2, and question D was 2 marks. Question 7 says a bacterial culture has area p millimeters squared at time t hours after the culture was placed onto a circular disc. A scientist states at time t hours, the rate of increase of the area of the culture can be modeled as being proportional to the area of the culture. And part A says show that the scientist's model for p leads to the equation p equals a e to the power of kt, where a and k are constants. Okay, so what does this mean if the rate of increase of the area is proportional to the area of the culture? Well, what's one way of stating the rate of increase of something? That's like the derivative, right? And they've told us the rate of increase is proportional to the area. So that's what we're going to start with for part A. So the rate of increase, as we've said, is the same as the derivative of the area with respect to, well, how do we measure the rate of something? That's in time. So it's the derivative of p with respect to time, and this is proportional to the area, which was p. Now, you know from other proportion questions that we can turn this into an equality by introducing some constant. So the derivative of p with respect to t will equal some constant times p. Okay, hopefully that's all making sense so far. Now we need to do a bit of algebraic manipulation, because if we want to get p equal to something e to the power of something, we need to basically make p the subject of this equation. And also we need to introduce a log somehow. So how can you see a log being introduced into this equation? Well, usually you get a log from taking the integral, right? So we need to do a bit of algebraic manipulation and then introduce an integral into this, and then hopefully we come up with e to the power of something. So firstly, what I'm going to do is to rearrange this so I have the p's on the left hand side and then the k and the dt on the right hand side. So therefore we can say that the derivative of p divided by p, so I've just divided by p on the left and then multiplied by dt on the right. So we get the derivative of p over p equals k dt. Then what we can do is take the integral of both sides. So that's just like multiplying by 1 on both sides, or anything to both sides. If you do the same thing to the both sides of the equation, it's still equal. So if we take the derivative of 1 on p with respect to p, so I've just written that slightly differently. dp over p is the same as 1 on p times dp. this equals the integral of, I think it's the derivative there, I meant integral of 1 on p with respect to p equals the integral of k dt. Now the integral of 1 on p with respect to p, that is going to be the log of p, and this equals the integral of k with respect to t. Well, this is just some constant, so we can write that as kt plus some constant c. Right, so this is, imagine this was say 3, the integral of 3 with respect to, say, t would be 3t. So we've taken the integral of both sides, and now we want p by itself. How do we get rid of a log? We raise that to the power of e. So if we raise both sides to the power of e, this would be p equal to e to the power of kt plus c. Another way of writing that, well, if you have, we'll think of your index laws. If you're adding two indexes, another way of writing it is p equals to e to the power of c multiplied by e to the power of kt. And c is a constant and e is just a number. So, a number to the power of a constant is some other constant. So we can replace this e to the power of c with a letter representing a constant. In the question they've used a, so we can use a. So therefore p equals a e to the kt. Alright, so just checking a to the kt we've got there. So a bit of algebraic manipulation and taking the integral was involved there. Fairly complex, I think, but hopefully that makes sense. Part B says the scientists measured the values of p at regular intervals during the first 24 hours after the culture was placed onto the disk. She plots a graph of the log of p against t and finds the points on the graph lie close to a straight line with a gradient 0.14 and vertical intercept 3.95. Part B says estimate to two significant figures the value of a and the value of k. Okay, so important information there is the gradient and the vertical intercept, or the y-intercept, and we're talking about the log of p, the graph of the log of p. Alright, so let's start B down here. Okay, now let's start by writing this equation out again. P equals a e to the power of kt, and we're talking about the graph of the log of p. So if we took the log of this equation, this would be the log of p equals the log of this, so the log of a e to the kt. Now the log of two things multiplied can also be written as the log of the first term plus the log of the second term. And as we said before, the log of e to the power of something, they cancel each other out. So this could also be written as the log of p equals the log of a plus kt. And we're told that the vertical intercept is 3.95. So let's just write that information down. That's an e in there. And the gradient is 0.14. Okay, so this is what we were graphing. This looks like a straight line equation, right? This would be the y-intercept. This would be the gradient of the variable, or the gradient times the variable. So using that idea, we can say if the vertical intercept is 3.95, therefore ln A equals 3.95, and k being what we'd use to represent the gradient of a straight line graph, k would equal 0.14. Now if the log of a equals 3.95, a is going to be e to the power of 3.95. Right, so I've just raised both sides to the power of e. E cancels out that log, so we're left with this e to the power of 3.95. If we put that into a calculator, e to the power of 3.95, we get 51.935 approximately. And it said find to two significant figures the value of a and k. So k is already two significant figures. So this one rounded to two significant figures would be 52. Okay, so there we've found k and a. For part B, part C says, hence show that the model for P can be rewritten as P equals a b to the power of t, stating to three significant figures the value of the constant b. Okay, so for part C, let's look at this equation again. P equals a e to the kt. So we know a and k now, so we can say P equals 52 e to the power of 0.14 t, and e to the power, we can say this is the same as e to the power of 0.14 to the power of t, so we can work this out. E to the power of 0.14 gives us 1.15. So this would be the same as writing 52 times 1.15 to the power of t. And therefore, b will equal 1.15 to three significant figures. Okay, so that was part C, the constant b. And then part D says, with reference to this model, interpret the value of the constant a for part 1, and part 2 says interpret the value of the constant b. Okay, so let's look at our model again. We've got p equal to 52 times 1.15 t. So for part D, the value of a, well, if t was equal to 0, then p would equal 52, right? E to the power of 0 would just be 1. So a then is going to be the initial area of the bacteria. What did they call it again? They called it the culture. So this was the initial area of the bacterial culture. So A is the initial area when t equals 0, and so then P equals 52 millimeters squared. Okay, so that's A. B is going to be the rate of increase. So for every hour, so when t equals 1, this area has increased by 52 times 1.15. When t is 2, we've effectively done that again. So we've multiplied the area after hour 1 by 1.15 again. So if you're multiplying something by 1.15, that's the same as increasing it by 15%, right? So this is the rate of increase per hour, which would be 15% per hour. So we can say B is the rate of increase per hour, or 15% per hour. I think rate of increase per hour gets you that 1 mark. So that was D part 2. And E says state a long-term limitation of the model for P. So this being an exponential model, it won't have any upper limit. So this would just go on increasing and increasing. You could put T equal to 1,000,000 and you get some large area. But we know that this bacteria exists in a circular dish. And so therefore there is some upper limit on the area, unless they keep putting it into larger and larger areas, but eventually there's going to be some upper limit on the area this culture can grow to, which the model does not account for. So we can state that in a sentence or two. So the long-term limitations, the area will hit a maximum, but this model does not account for that. And the maximum being the size of the dish. Okay, so that was question 7. A was 4 marks, B was 3 marks, C was 2 marks, D was 2 marks, and E was 1 mark. Question 8 starts with a diagram and it says a bowl is modeled as a hemispherical shell as shown in figure 3. Initially the bowl is empty and water begins to flow into the bowl. When the depth of water is h centimeters, the volume of water V centimeters cubed is according according to the model, is given by v equal to a third pi h squared multiplied by 75 take h, where h is between 0 and 24. The flow of water into the bowl is at a constant rate of 160 pi centimeters cubed per second for h between 0 and 12. Part A says find the rate of change of the depth of the water in centimeters per second when h equals 10. So part A, they've given us the constant rate or the change in the volume per second of 160 pi. Another way of stating that would be the change in volume with respect to time, or dv on dt, is 160 pi. And we're looking for the rate of change of the depth of the water. Now the depth of the water, they said, is h, so we're looking for dh on dt. Okay, and they've given us an equation in terms of v and h. So we don't have an equation in terms of h and t. So we need to think algebraically here. We need to think, how can we relate these two rates of change together through this equation? So we can start off by taking the derivative of this equation with respect to h, and then do some algebraic manipulation to get dh on dt out of that. So hopefully this starts to make sense as I go through it. So dv on dh we can work out using this equation. So take the derivative of this. Actually, it might be helpful to expand it out first. So another way of writing v would be, if we expand out these brackets, we would do 75 divided by 3, right? A third times 75. That would be 25 pi h squared. Take a third pi h cubed. H squared times h is h cubed. So I think it's going to be easier to take the derivative of the equation in that form. So let's go ahead and do that. So we can use the power rule. When you've got an exponent, bring it down the front and then subtract 1 from it. So 2 times 25 would be 50 pi times h. Take 3 times 1/3 is just 1. So this is going to be pi h squared. Okay, so now we have dv on dh. How can we relate that to dh on dt? Well, let's think for a minute. We are also given dv on dt. So using those three terms, dv on dt, dv on dh, and dh on dt, we can relate them all together and we'll come out with an equation we can solve for dh on dt. So we can say dv on dt, which we have here, equals dv on dh multiplied by dh on dt. Right, so looking at this right hand side, what we've actually introduced is this dh over dh. So if I was to cancel that out, I'd be left with dv on dt. So using that idea, we can relate these three things together. So dv on dt was 160 pi. This equals dv on dh, which we have here, which is 50 pi h take pi h squared, multiplied by dh on dt, which is what we're looking for. And then if you look at this, they've given us a value for h. Once we plug that in, we'll have one unknown, which is dh on dt. We'll be able to solve that equation for dh on dt. So let's go ahead and get started on that. So when h equals 10, if we plug that in here, I might rearrange this to write it as dh on dt equals, we'll have 160 pi as the numerator, and then the denominator will be all of this with 10 plugged into it. So 10 multiplied by 50, that's 500 pi. and then 10 squared is 100, so this will be take 100 pi. So then this equals 160 pi on 400 pi, or 160 on 400, because those pi's will cancel out. So this is 160 on 400, 16 on 40, cancel the 4's, 4 on 10, 2 on 5, which is 0.4 centimeters per second. So h was in centimeters, so this will be centimeters per second. Okay, you can also just put that straight into a calculator, 160 on 400, and it will come out to 0.4. So there we go, we have found dh on dt. That was a tricky step, I think. I think that would be where most people would get stuck, how to relate the derivative of v with respect to h to dh on dt. And that's a key skill that you should try to develop, is how to manipulate these derivatives and, you know, calculus expressions in general to get the derivative that you want. Okay, so that was part A. Part B says, given that the flow of water into the bowl is increased to a constant rate of 300 pi centimeters cubed per second for h between 12 and 24, find the rate of change of the depth of the water in centimeters per second when h equals 20. Okay, so this is only 2 marks because we've done all the hard work already. We already have an expression for dh on dt, and all we need to do is change this 160 pi to 300 pi and h to 20. So for part B, I'm looking at this expression here, dh on dt. This 160 pi changes to 300 pi, and this denominator here would be 20 times 500 now, which is 1000 pi. Take 20 squared is 400, so this would be 400 pi. And then we have 300 pi over 600 pi, or 300 over 600, again because those pi's cancel out, and that's obviously a half, so 0.5 centimeters squared per second for part B. Okay, so question 8, part A was 5 marks and part B was 2 marks. Question 9 says a circle with center A 3, -1 passes through the point P, -9, 8 and the point Q, 15, -10. Part A says show that PQ is a diameter of the circle. Okay, so what do you know about the diameter? So it needs to pass through the center. So if PQ is a diameter, the midpoint should be the center of the circle. So we can use the midpoint formula to prove that it's a diameter. So for part A, think back to GCSEs. How do we find the midpoint of a line? We need to do the average of those differences, right? So x1 plus x2 over 2 and y1 plus y2 over 2 will give us the coordinates of the midpoint. So looking at P and Q, we've got -9 plus 15 over 2, and it doesn't matter what order you do them around as long as you have them in the same order for each point. So if this is x1, this is y1, so I've got 8 plus -10 over 2, and then we just need to simplify this. So -9 plus 15, that's 6 on 2, which is 3. 8 take 10 is -2 over 2, that's -1. This equals the center of the circle, 3, -1. So we can say something like, as the midpoint of PQ is the center of the circle, PQ must be the diameter. Okay, so there we go, that's part A for 2 marks. Part B says find an equation for the circle. Okay, so let's start with the general equation for a circle, and that is x take a squared plus y take b squared equals r squared. This is where AB is the center of the circle, and R equals the radius. Sorry, R is the radius. So we actually know what the left-hand side of this equation will already look like because we have the center of the circle, but we need to find the radius. We can find this using the distance formula. So the distance of A to either of these 2 points, I'll choose P. That will give us the radius. So the distance of AP is going to be the square root of the coordinates subtracted by each other. So this is basically the Pythagoras' theorem. We can do x2 take x1 squared plus y2 take y1 squared. Okay, so using those 2 points, I should have written them down somewhere. We've got -9 take 3, -9 take 3 squared plus 8 take 1 squared. 8 take -1 will be 8 plus 1 squared. Okay, then this is going to be the square root of -9 take 3 is 12 squared, that's 144, plus 8 plus 1 is 9 squared, that's 81. This is the square root of 225, which is 15, but we don't really need to write that because we want r squared. So r squared, if the radius, okay, let's just write it down. If the radius is 15, we need to square it again to get this term here, so it would be 225. So therefore, the equation is x take A was 3, so the center, remember, is 3, -1. Now it's important what you do with these negatives here. If it's a positive, it stays negative. And if it's a negative, you need to turn this into a positive. So it's opposites world here in equations of circles. And this equals the radius squared, as we said, is 225. So there is the equation of the circle for part B. And part C says a point R also lies on the circle. Given that the length of the chord PR is 20 units, find the length of the shortest distance from A to the chord PR. Give your answer as a surd in its simplest form. Okay, so you need to be familiar with finding the distance from the center to a chord. And this is like finding the other leg of a right angle triangle. And I'll explain a bit about that in a minute. So we said the radius was 15. So the shortest distance from the center to a chord and you also need half the length of the chord. So the chord divided by 2. They said the length of the chord is 20, so this is 10. The shortest distance from the center to the chord is the square root of the radius squared take half the length of the chord squared. And I can demonstrate quickly why that is. So if we draw a circle here, having trouble here, okay, there we go. So this is the distance we're looking for. So because it's perpendicular, it's cutting that chord in half. This length is half the length of the chord, which we said was 10. This is the length that we're looking for. What about this distance from the center to the end of the chord? That's the radius, right? Which we know is 15. This forms a right angle triangle, and you know to find the missing leg of a right angle triangle, you do the hypotenuse squared, take the other leg squared, and take the square root of that. So that's where that formula comes from. So we just need to go ahead and simplify this. This is going to be the square root of 225 take 100, which is the square root of 125, which is 25 times 5. The square root of, okay, let's just write that out. The square root of 25 times 5 and the square root of 25 is 5, so this can be written as 5 times the square root of 5. And that was in, did they give us units for those? They just said units, so we don't need to include units in our answer. And that is in simplest form. There's no further way we can simplify the square root of 5. So that was part C. Part D says find the size of angle ARQ, giving your answer to the nearest 0.1 of a degree. Okay, my brain is crying out for a diagram here to picture what this angle is. So I'm going to draw a bit of a diagram for part D. Okay, so nice big circle, and we're looking for ARQ. PQ we said was the diameter, A is the center, and R was some other point on the circle. Okay, so let's draw in PQ first. So let's say that's PQ. A was the center. R was some other point on the circle. So that PR was 20. And we're looking for the angle ARQ. Okay, so let's draw in RQ as well. Now, this being the diameter, we know something about the angle PRQ. That is an angle in a semicircle, and angles in a semicircle are always 90 degrees. Okay, so that might help us a little bit. And then let's draw in AR as well. And we're looking for that angle in there, ARQ. All right, so let's look at this carefully and see what might help us find that angle. One thing I know is that this is the radius, AP, AR is the radius, and AQ is also the radius. And then as soon as I draw in those lines, I'm seeing that this triangle ARQ must be isosceles. So therefore, these two angles here must be equal, right? The base angles of an isosceles triangle are always equal. So AQR or even PQR is equal to ARQ. The other thing I know that I haven't written in yet is PQ is 30 units long, because that's the diameter, right? 2 lots of the radius is 30. This is a right angle triangle. So this angle in here, PQR or AQR, I can find using the trigonometric ratios, right? So what would I need? What ratio would I need there? I need the opposite over the hypotenuse. So that would be the sine ratio. So the sine of angle PQR would be the opposite side, 20 over 30. And we've said that's equal to ARQ, so therefore the sine of ARQ will also equal this, 20 over 30. So we can say the sine of ARQ will equal 20 over 30 as well. And that's because triangle ARQ is isosceles. Okay. Then you can see you can solve for angle ARQ by taking the inverse sine. So angle ARQ will equal the inverse sine of 20 on 30. So let's put that into a calculator. Inverse sine of 20 on 30, or even 10 on 15 would do. Divided by 30 equals 41.81. Approximately 41.81. Was there a degree of accuracy? 0.1 of a degree, so we need to round this off to 41.8 degrees. Okay, so that was part D. Part A was 2 marks, part B was 3 marks, C was 2, and D was 2. And that was question 9. Question 10 starts with a diagram, and it says figure 4 shows a sketch of the curve C with parametric equations x equal to the log of t plus 2 and y equals 1 on t plus 1, where t is greater than negative 2 on 3. Part A says state the domain of the values of x for the curve C. So the values of x will have a certain range because they've given us a range for t. So if t is greater than -2 and 3, if we substitute that in here, we'll have the domain of x. So for part A, we'll say that x equals, greater than, x is greater than the log of -213 plus 2. Right, so I've just substituted that minimum t value into the equation for x. So then x is greater than the log of -2/3 plus 2. That'll be like a positive 1 1/3. Another way of writing that is 4 and 3. So I think we can leave it as that. We probably don't need to expand that out or anything. So that should be good for the domain for 1 mark. Part B says the finite region R shown shaded in figure 4 is bounded by the curve C, the line with equation x equals the log of 2, the x-axis, and the line with equation x equals the log of 4. Part B says use calculus to show that the area of R is log 3 on 2. Okay, I'm going to go ahead and say this is a difficult question. It's worth 8 marks. I think it deserves those 8 marks. And I think there's going to be a lot of difficult steps involved here. So firstly, let's recognize some of the problems we've got here. So to find the area under a curve, you want the equation of that curve with respect to x, or in other words, you want the integral of y with respect to x. So we have the parametric equations, but we don't have y in terms of x. So that's the first problem, getting this integral of y dx. So one way you could do this is to rearrange the equation for x and substitute it into the equation for y. Another way you can do this is to actually kind of manipulate the terms, the integral terms a little bit, so that you actually get an expression for the integral of y with respect to dx without actually having to rearrange these equations. That's the way I'm going to go, but you can do it the other way and it will work out perfectly fine. So firstly, what's one way you know of getting dx? How do we get that term? Well, usually you would take the derivative to get dx, right? So that's what I'm going to start with, finding the derivative of x with respect to t, and then hopefully we can manipulate it a little bit to get dx by itself. So let's start by taking the derivative of this equation for x. So dx on dt is going to be the derivative of the log of t plus 2. The derivative of a log is 1 over what's inside that log. So this is going to be 1 over t plus 2. And then we can say, well, if we're looking for the integral of y with respect to x, but we have this equation, 1 on t plus 1, this would be in relation to dt. But if we insert a dx on dt here, that would cancel with this dt, and then we'd end up with the integral of y with respect to x. So if we insert this dx on dt into this integral, we'll actually end up with the integral of y with respect to x. So this is going to be the integral of y, which is 1 over t plus 1, multiplied by the derivative of x, which is 1 over t plus 2. And then we still have that dt here. So even though we're taking integral with respect to t, this is equivalent to the integral of y with respect to x. That's kind of a confusing point, but hopefully you can see that in this expression, those dt's effectively get cancelled out. So let's continue with this. So we're looking for this integral now, 1 over t plus 1 multiplied by 1 over t plus 2, which is equivalent to saying the integral of 1 over t plus 1 times t plus 2. And now this is going to be difficult to integrate, but if we change this into partial fractions, then it's going to be a lot easier. So if we look for the partial fractions, in order to split this into two fractions, something over t plus 1 plus something over t plus 2, then that's going to make our lives a lot easier. So we can write this as a over t plus 1 plus b over t plus 2. And this is another difficult step. Partial fractions are sometimes quite difficult to figure out. So along with this first step of figuring out the integral of y dx, we also have the partial fractions. So then we can say this equals 1 over, or this basically, so t plus 1 times t plus 2. So I didn't mean to write that equal sign there. So to figure out the partial fractions, we say that a over t plus 1 plus b over t plus 2 equals this. Therefore, if we rearrange this, if we multiplied the left-hand side by this denominator here, we would have a times t plus 2 plus b times t plus 1, right? So those denominators would cancel with the t plus 1 and t plus 2 in this denominator, and this would equal 1. And then comes another difficult part. So we've effectively got three unknowns here that we need to figure out, except we know that the t's need to cancel each other. So this t needs to cancel with this t. The only way that's going to happen is if a and b are negatives of each other. And also we know that we need a 2 take 1 to equal 1. So that means that a and b can only really be 1, and 1 needs to be a negative of the other. So you could try it with something else. So you could try 2 t plus 2 take 2 t plus 1 and see what that equals. You'd get 2t take 2t, they would cancel out, but then you'd have 4 take 2, which would equal 2. So the only numbers there that fit are 1 and negative 1. So we can say this is equivalent to the integral of 1 over t plus 1 take 1 over t plus 2 with respect to t. Now this integral is going to be a lot easier to find because we know the integral of 1 over something such as a linear expression such as t plus 1 is the log of that thing. So this is equal to the log of t plus 1 take the log of t plus 2 plus some constant c. And then now we've got the integral, we can look for the definite integral from log 2 to log 4. So we can say the area R is equal to log of t plus 1 take the log of t plus 2 from log 2 to log 4. Now actually I made an error there, because if we have this integral in terms of t, let's go back to the question quickly. It says x equals log 2 and x equals log 4. So we actually have to find the value of t when log equals 2. So if x equals log 2, that means t would be 0. If x equals log 4, that means t would be 2. So we're actually looking for the integral when from t equals 0 to t equals 2. So I'll just correct myself there. So it's actually from 0 to 2. So then we can substitute those in and subtract them from each other. So this is going to be log of 2 substituted in here. So 2 plus 1 is 3. Take the log of 2 plus 2 is 4. Subtract, substituting 0 in. So this is going to be the log of 1. Take the log of 2. All right, almost there. Then we've got the log of 3, take the log of 4. Another way of writing when you're subtracting logs is to divide those terms. So this is the log of 3 divided by 4. Subtract, the log of 1 is 0. So we're going to have subtract negative log 2, which is plus log 2. And when you're adding logs, another way of writing that is multiplying those terms. So this is the log of 3 on 4 times 2. And then that 2 would cancel with this 4, so we'd end up with the log of 3 on 2, which is what they want us to find. Alright, so a difficult question, quite a lot of difficult steps, hard to see how to get through all of those steps, but hopefully that solution made sense. I will say that there are at least 6 different ways of doing this or finding this solution. There's different ways of finding this integral, y with respect to x. There is the way of substituting x into y and finding that integral. You end up having to find the integral of 1 over e to the power of t plus 1, I think it was. Sorry, e to the x. So that's difficult. There's at least 4 ways of doing that integral. So there's at least 6 plus different ways of getting the solution, which in an exam I think is actually a problem, because if you have a marker that is just following the mark scheme, you might have a correct solution, but that marker may not recognize it if it's not on the mark scheme. However, a difficult question, deserving of that 8 marks, and if you have a different solution, please share it in the comments. I'm sure people would find that useful. Okay, so there you go. That was question 10. A was 1 mark, B was 8 marks. Question 11 says the second, third, and fourth terms of an arithmetic sequence are 2k, 5k take 10, and 7k take 14, respectively, where k is a constant. Show that the sum of the first n terms of the sequence is a square number. Okay, nice to get a less wordy question. Those wordy questions get a bit tiring after a while. So we're looking for the sum of an arithmetic sequence. So that formula is actually in your formula booklet. So it looks like this: a half n multiplied by 2a sub 1 plus n take 1 times d. And this is for when you don't know the last term of the sequence, such as in this case where we're looking for the first n terms. Now the terms in this formula are a1, a sub 1 is the first term, n is the number of terms, and d is the common difference between those terms. Okay, so looking at this formula, hopefully you see there's something we're missing. So there's 2 things we're missing. We don't have a sub 1, and we don't have the common difference between the terms. But we can find that common difference using these terms they've given us. So how do you find the difference between 2 terms? Well, you just subtract them, right? So we can subtract the third and the second term. So 5k take 10 take 2. So this was the third term, this is the second term. This equals 5k take 2k is 3k take 10. Alright, so that's not helping us a lot yet, but we also have a fourth term. We can find the difference between the fourth and the third term, and that should also equal the difference between the third and the second term, because they've told us this is an arithmetic sequence, meaning there is a common difference between each term. So let's go ahead and do that. 7k take 14, take 5k, and that should be in brackets, take 10, because we're subtracting that whole term itself. And this is going to equal 7k take 5k is 2k, and then negative 14 subtract negative 10, that'll be negative 14 plus 10 will be negative 4. So then we can say that 3k take 10 must equal 2k take 4. Again, because these are the common differences, we can say they must be equal. Then we can solve for k. So subtract that 2k from the left hand side. 3k take 2k is k. Add that negative 10 to the right hand side. Negative 4 plus 10 is 6. So we end up with k equal to 6. Then we can figure out these second, third, and fourth terms. So let's write down a list quickly. I think that's the easiest way to do it. So the second term, 2 times 6 is 12. The third term, 5 times 6 is 30, take 10 is 20. The fourth term, 7 times 6 is 42, take 14, that's 28. Okay, so now we can see 12 to 20 is 8, 20 to 28 is 8, so the common difference, D, is going to be 8. And then the first term, 12 take 8, that's going to be 4. Okay, so now we have A1 and D. We could go ahead and solve Sn. This is going to be half n multiplied by 2 times A1. A1 was 4, plus n take 1 times the common difference, which we said was 8. And we should write that down actually. A1 equals 4, D equals 8. Okay, let's go ahead and simplify this now. So this is a half n multiplied by 8 plus n take 1 times 8. So this would be 8n take 8. Then keep simplifying. So 8 subtract 8, they would cancel out. Then we would have half n times 8n. In other words, a half of 8n, so 4n. And then n times n is n squared. So 4n squared. Another way of writing that would be to square, or in other words, you can write 4 as 2 squared. So this could be rewritten as 2n all squared, would evaluate to 4n squared. And going back to the question again, I've forgotten actually what they were asking. Show that the sum of the first n terms of the sequence is a square number. Okay. This is clearly a square number. Whatever n is, we'll square it and we'll end up with a square number. So all we really need to finish with is a statement. Therefore, the sum of the first n terms will always be a square number. Okay, so there you go. That was question 11 for 5 marks. The marks there were solving for k, 2 marks in there, and then the formula and substituting into the formula, finding the common difference, finding the first term, and then showing that it's a square number. So 5 marks in total for question 11. Question 12 says a curve C is given by the equation sin x plus cosine y equals 0.5, where x is between negative pi and 2 and 3 pi and 2, and y is between negative pi and pi. A point P lies on C. The tangent to C at the point P is parallel to the x-axis. Find the exact coordinates of all possible points P, justifying your answer. Okay, so tangent, we need to find the derivative of this curve. So the curve C is given by this equation, so we want to find dy on dx. That's going to give us the equation for the tangent. And they also tell us the tangent is parallel to the x-axis. That's telling me that dy on dx will equal 0. So when the tangent is parallel to the x-axis, that means it's horizontal. The gradient of that line is 0. So dy on dx will be 0. Okay, so I want to find the derivative of this equation, and I'm going to use implicit differentiation here. I don't see any other way to do it, but maybe there is. However, that's the way I'm going to go, implicit differentiation. So we need to take the derivative of each term with respect to itself, and then rearrange to get dy and dx. Okay, so we're looking for the derivative of sine x with respect to x. and then the derivative of cosine y. Now we need to find everything with respect to the same thing. So we're going to start by writing this. Derivative of cosine with respect to x won't give us much. Oops, and then I need to write it here. So derivative of 0.5 with respect to x, and we can rewrite this slightly differently. So we're looking for the derivative of sine x. Well, that's cosine x, so I can just do that firstly. And then if we want the derivative of the cosine y with respect to y, we can do that. So this is with respect to y of cosine y, but then we need to introduce a dy on dx to cancel that out, right? So if I introduce a dy down here, I need one in the numerator as well. So I haven't changed anything. It's effectively the same as multiplying by 1, but what the end result is that I have a dy and dx over here, and I can this cosine y with respect to y. The derivative of 0.5, well, that's just 0, that's just a constant. And so now I can say this will be cosine x plus the derivative of the cosine is negative sine y times dy and dx equal to 0. And then make dy on dx the subject of this equation. So dy on dx would be, we'll subtract that cosine x from the right hand side. So we'll have negative cosine x over on the right hand side here, and then divide by this negative sine y. So this will be negative sine y over here. And then those negatives would cancel out, so I didn't really need to write those. So dy and dx, cosine x over sine y. Okay, and then, so we're looking for the coordinates of all possible points of P. So remember we said that when the tangent is parallel to the x-axis, so the gradient of the tangent, when it's parallel to the x-axis, it will be 0. So the gradient of the tangent at P equals 0. So therefore dy on dx equals 0. So therefore cosine x over sine y equals 0. Then we can just multiply this sine y on the right hand side and we can get rid of it. So therefore cosine of x equals 0. And then we can find some x coordinates. So we know the domain of x was negative pi on 2. Was it less than or equals to? So x was greater than or equal to negative pi on 2 and less than 3 pi on 2. So that's going to figure into our answers here. So that when the cosine of x is 0, we can say x equals pi on 2, but the cosine of x also equals 0 at pi on 2 plus k pi. So 3 pi on 2, 5 pi on 2, etc. We'll still get cosine of x equals 0. So we need to add on this k pi, where k is any integer, and it can also be a negative as well. So pi on 2 take pi would be cosine, would give us the cosine of x equals 0. So looking at our domain now, what are the possible values of x? Well, we know pi on 2 is 1, because that fits in our domain. Actually, it might make this easier to draw a unit circle. So pi on 2 is up here, and if you think of the cosine as the x value, then this is where cosine of x equals 0, pi on 2. It also equals 0 down here, and this is 3 pi on 2 if I go around this way. But if I start here and go around this way, it's also negative pi on 2. And the range is that x is equal to negative pi on 2, greater than and equal to. So x could also be negative pi on 2, but it's only less than 3 pi on 2. It's not less than or equal to. So 3 pi on 2 is not a solution here. So these will be the only two solutions of x, pi on 2 and negative pi on 2. Okay, so we have the possible x coordinates of p. Now we need the y coordinates, and we can substitute in the x coordinates into our original equation to find the y coordinates. So let's write that down here so we just have something to refer to. We had sine x plus the cosine of y equals 0.5. So let's firstly start with when x equals pi on 2. Therefore, we'd have the sine of pi on 2 plus the cosine of y equals 0.5. So you can see here we're going to be able to solve for y, and we need to know the sine of pi on 2. Well, if the cosine of pi on 2 is 0, then the sine of pi on 2 must be 1. So it's 1 plus the cosine of y equals 0.5. Then the cosine of y is going to be 0.5 take 1, which is negative 0.5. And now we need to know our absolute values of certain angles. And one way to help you remember these is these right angle triangles of pi on 6 and pi on 3. So pi on 6 and pi on 3 have absolute values you need to know. And this triangle is 1, 2, root 3. That's the sides. That's a right angle triangle. And if you can remember the trigonometric ratios, then you know the cosine of these angles. So the cosine is the adjacent side over the hypotenuse. So 1 over 2, which is the same as 0.5. So the cosine of pi on 3 is a half. So therefore, we've got y equal to... So when is the cosine function a negative value? Again, let's look at the unit circle. And here you need to think of the quadrants. So in which quadrants is the cosine function negative? Again, if you think of the cosine function as the x, if you think of this as the x-axis, well, the x values are negative over here, right? In quadrant 2 and quadrant 3. So this is our, pi on 3 is our reference angle. So I should write that down actually. So let's move this down here. So let's say our reference angle equals pi on 3. And we've already said we're talking about quadrant 2 and quadrant 3. So that means the angle away from the x-axis is pi on 3. Right, so that's what the reference angle means, and therefore y is going to be pi take pi on 3. So y is actually this angle in here, starting from 0. And if we look back at the range of y was negative pi to pi. Okay, so let's write that down here. Negative pi to pi was the range for y. So therefore, that means this angle will be within the range, and also this angle around here will be within the range. So then the two possible values for y will be pi take pi on 3, and then this angle is going to be negative pi take pi on 3 as well. So negative pi take pi on 3. Actually, that's a plus pi on 3, isn't it? Yes. So we're at negative pi, we add on pi on 3 to get this angle here. Okay, so plus pi on 3. All right, so pi take pi on 3, well, that's like 1 take a third. That's 2/3. 2/3 pi, or 2 pi on 3. And then the same thing for this one. So negative 1 plus a third is negative 2/3 pi, or negative 2 pi on 3. Okay, so we have our two y values, we have our two x values. They're the only possible solutions within the ranges they've given us. Oh, we haven't done x equal to negative pi on 2 yet. We've only done x equal to pi on 2. So we need to do this this other x value as well. Almost forgot about that. So when x is equal to negative pi on 2, we'll have sine of negative pi on 2 plus the cosine of y equals 0.5. The sine of negative pi on 2, that's negative 1, plus the cosine of y equals 0.5. And then therefore the cosine of y would equal 0.5 plus 1, 1.5. But that's not possible. The cosine function can't be greater than 1. And you know that if you've ever looked at the graph of this function, the maximum and the minimum values are 1 and negative 1. So this solution is not possible. So we could say cosine of y cannot be greater than 1. So therefore, we have all our possible coordinates, and we just need to write them down in our final answer. So the possible coordinates for P will equal pi on 2, what were they? The y values were 2 pi on 3, and pi on 2, negative 2 pi on 3. You might think that's a bit strange. So if the x coordinate's the same, how can we have two of the same y coordinate? And it just means that it's it's some kind of circular sort of object, and it has two solutions at pi on 2. So you could go ahead and put that equation into a graphing calculator and see what it looks like, and you'll get a nice visual for this graph, and you'll see how that fits in. But there you go, they're the possible coordinates for P, and that was question 12 for 7 marks. Question 13, part A, says show that the cosecant of 2x plus the cotangent of 2x is equivalent to the cotangent of x when x is not equal to 90 n degrees, where n is an integer. Okay, so let's have a look at the left-hand side of this equation. So for part A, the left-hand side is the cosecant of 2x plus the cotangent of 2x. That's it. So another way of writing this, well, the cosecant is, the definition of the cosecant is 1 over sine x. So if it's 2x, then it's going to be 1 over sine of 2x. The definition of the cotangent is 1 over tan x. So I'll just actually write that over here. So the cotangent of x is 1 over tan x. Another way of writing that, well, the tangent is sine over cosine. So 1 over the tangent is the cosine of x over the sine of x. So I might use that expression because I can see, well, the denominators will be the same, and then I'll be able to combine them. So the cotangent of 2x is the same as the cosine of 2x over the sine of 2x. So now we have the same denominator. We can combine these fractions. So this is going to be 1 plus the cosine of 2x over the sine of 2x. And I'll just reference back to the original equation. We have the cotangent of x, so we don't have 2x on the right hand side here. So what I want to do to get rid of these 2x terms is to use the double angle formulas. So the double angle formula for the cosine of 2x is 2 cosine squared x take 1, and that's in your formula booklet. The double angle formula for the sine of 2x is 2 sine x cosine x. Okay, let's keep simplifying this. 1 take 1, they would cancel out, so we're just left with 2 cosine squared x. One of those cosine x's could cancel with the one on the bottom line, So cosine and 1 cosine cancel out. So we're just left with 2 cosine x on the top line and 2 sine x on the bottom line. The 2's would cancel out. So we're just left with cosine x over sine x. And as we said before, that's equivalent to the cotangent of x. So we can say this is equivalent to the cotangent of x, which is equal to the right-hand side. So there we go. There's our proof, our show that, for 5 marks for part A. Part B says, hence or otherwise solve for theta between 0 and 180, the cosecant of 4 theta plus 10 plus the cotangent of 4 theta plus 10 equals root 3. Hopefully you can see these two things must be related. So we've got the cosecant of 2x and the cotangent, and here we've got cosecant and cotangent equals root 3. Now when you see a root 3 and you're talking about trigonometry, hopefully you can see, okay, there must be an angle related to that root 3. If you know your absolute values for certain angles, you know there's a root 3 related to pi on 3 and pi on 6, or we're talking about degrees here, so it'll be 30 and 60 degrees. So we're going to be able to relate that root 3 to an angle. But let's get started on part B down here. So the first thing, actually, let's just write out that whole expression again. So it was 4 theta plus 10 plus the cotangent of 4 theta plus 10 equals root 3. Just double check that. Okay. Now we were talking about 2x here. And you can see these angles have a factor of 2. So another way of writing this is the cosecant of 2 times 2 theta plus 5 plus the cotangent of, oops, that should be 2 times 2 theta plus 5 equals root 3. And what we showed in part A was that if we have this expression, cosecant 2x plus cotangent 2x, this can be rewritten as the cotangent of x. So in this case, our x is just 2 theta plus 5, right? So here we had some x, and in this expression, it turns out our x is 2 theta plus 5. So we can rewrite this as the cotangent of x, 2 theta plus 5, equals root 3. Now here is where I was talking about these absolute values for an angle. So root 3 does turn up for the tangent function, and again I'm going to draw this right angle triangle for pi on 3 and pi on 6 because I know there's a root 3 in there. So this this right angle triangle has sides 1, 2, root 3, and the cotangent, as we said before, is related to the tangent function, and the tangent function is the opposite side over the adjacent side. So the tan of pi on 3, for example, is root 3 on 1, or root 3. So the cotangent actually would be the opposite of that, would be 1 on root 3. So therefore, the cotangent of pi on 6 must be root 3. So the tangent of pi on 6 would be 1 on root 3. Therefore, the cotangent of pi on 6 would be root 3. Oh, I just realized I'm meant to be talking about degrees. So pi on 6 is 30, pi on 3 is 60. So this is actually 30 and 60 degrees. Sorry about that. So this one was 60 and 30. Okay, so the cotangent of 30 degrees equals root 3. So therefore, if we've got the cotangent of 2 theta plus 5 equals root 3, so the reference angle equals 30 degrees. So again, I'll draw a unit circle to explain what I mean. And we need to think about where the cotangent function is positive. Because we have a positive answer, it will be in the quadrant where the cotangent function is positive. If you have a better memory than me, maybe you can remember in which quadrants it's positive. I generally only remember the sine and the cosine, and I need to get better at that. But if the cotangent function is positive, that means the sine and the cosine are either both positive or both negative. So they're both positive in quadrant 1, and they're also both negative in quadrant 3. So the cosine is negative and the sine is negative. That would give us a positive cotangent. So our reference angle is in quadrant 3, so 30 degrees, quadrant 1, and also quadrant 3. Okay, so that means this term, this 2 theta plus 5, will equal 30. So let's write that over here. 2 theta plus 5 will equal 30. It will also equal 180 plus 30. So this is 180 degrees, and then we need to add on that extra 30 of the reference angle. So we can say that it's also equal to 180 plus 30. Okay, and then we can solve both of these for theta. So 2 theta will equal 25. Therefore, theta equals 12.5 degrees. And then 2 theta equals 180 plus 30 is 210. Take 5 would be 205. And therefore, theta equals 102.5 degrees. Okay, so two possible values of theta. Just want to check. So theta was between 0 and 180, and they both fit in with within that range. So they're both fine. So the difficult part of that question, I guess, was equating that 2 theta plus 5 to 30, and also using that as a reference angle. So also accounting for the other possible answer for theta. Okay, so that was part B for 5 marks, and question 13 for a total of 10 marks. Question 14, part I, says Caden claims that 3 to the power x is greater than or equal to 2 to the power x. Determine whether Caden's claim is always true, sometimes true, or never true, justifying your answer. Okay, so part I, well, for all positive values of x, this will be true. So 3 squared is greater than 2 squared, 3 cubed is greater than 2 cubed, etc. But if if x is 0, 3 to the power 0 is 1, 2 to the power 0 is 1, that'd be equal. So that's still true. That'd be equal. But then if x is a negative 1, this would be 1/3 over 1/2. And actually a half is greater than 1/3. So it would not be true if x was negative 1. So we could say if x equals negative 1, 3 to the x equals 1 on 3, 2 to the x equals 1 on 2. So therefore then we'd have 2x greater than 3 to the power x. So I would say this is sometimes true. So when x is greater than or equal to 0, then it's true. But if x is less than 0, then it's not true. So, so therefore, we could also give an example. X equal to 1, 3x is greater than 2x. So to show that we see that it's sometimes true. So therefore, Caden's claim is sometimes true. And it might be worth checking the mark scheme there to see if that's enough for 2 marks. You might need an extra example or something or more information, but I think that should be enough. Part 2 says prove that root 3 is an irrational number. Okay, this is going to be tough if you've never seen a proof of an irrational number before. So it really would help if you've seen, say, the proof that root 2 is irrational. It's pretty much identical to this one, So I wouldn't blame you if you hadn't seen that before. It's hard to know how to do this, but we start off by saying that it's going to be proof by contradiction. So this is saying, well, if it is a rational number, then we get a contradiction. So we can start by saying let root 3 equal a over b. If root 3 is a rational number, then it must equal some fraction where a and b are integers, right? So that's the definition of a rational number. It can be written as a fraction. So then we can say therefore 3 equals a squared over b squared. So I just squared both sides. So therefore then a squared would equal 3b squared. And then, so I just multiplied the left-hand side by b squared. Now, a fact about square numbers is if a square number is has a factor of 3, then the square root of that number will also have a factor of 3. And you can look at the square numbers and realize this is true. So if you look at, say, I don't know, 3, 6, 9, 12, 3 squared is 9, 6 squared is 36, 9 squared is 81, 12 squared is 144. 3 goes into all of these numbers. 3 also goes into the square of those numbers. So we can say a squared is a multiple of 3, or actually another way of stating that is it's divisible by 3. And therefore a is also divisible by 3, as we stated. So then, therefore, we could write a as 3 times some other integer. So if 3 is a factor of a number, you can write that as 3 times another integer. For example, 6 could be written as 3 times 2, 9 could be written as 3 times 3, so we can always write that as 3 times some other integer. So then we can substitute that in to this equation up here. So I'll just put a star there. So we're using this one up here. So therefore, 3 equals, when we get to a squared, we'll put in 3c. So we'll have 3c squared over b squared. So therefore, if we rearrange this, we'll have b squared equal to 3c squared, right? So if I multiplied b squared over here, divided, this would be 9c squared, and then divided by 3, we'd end up with 3c squared. Therefore, b squared is also divisible by 3, and therefore b is also divisible by 3, as for a, the same idea. And now we have a contradiction, right? We said root 3 was equal to a on b in simplest terms. So we said these two integers were not sharing any factors. It was the simplest possible fraction. But we also know that a and b are both factors of 3. So we have a contradiction there, and that contradiction implies that root 3 cannot be written as a rational number. So that's the idea behind proof by contradiction. So let's finish this off. So let's say, therefore, a and b are both divisible by 3, or have factors of 3 or multiples of 3, however you want to state that. So therefore, this contradiction implies that root 3 cannot be written as a rational number. Okay, so there is the proof that root 3 is not, an irrational number. As I said before, tough if you haven't seen that type of proof before, but if you have, it should be okay. That 6 marks should be okay for question 14. And that was the end of the paper. That was question 13, 14 for 8 marks. Total of the paper was 100 marks. I'd be really interested to know what you thought of this if you had a go at it yourself. I think the standout question in there was question 10. I thought that was quite challenging. But I'd be really interested to know if you've done other past papers, how you think that compares to other past papers. If you found any of this challenging, which questions you thought were the hardest. And if you found this video useful, please leave a like. If you want to see more content, please subscribe, and I'll see you in the next one. Bye for now.